This animation shows our core problem, combining a fully populated sorted list with a second sorted list. Notice that the first array has precisely enough empty, transparent space at the end to hold all the elements from the second array. The beginner's instinct is to merge starting from the front, but if we grab a number from the second list and place it at the first index of the top list, we immediately overwrite and destroy active data. To prevent that data loss, you have to shift everything else one space to the right. Repeating this chain reaction for every single insertion forces the computer to do massive amounts of unnecessary work. We can bypass this bottleneck entirely by reversing our perspective. Notice that the empty slots are located at the very end of our target array. By working backward from the highest numbers to the lowest, we avoid overwriting active data. We turn a messy, expensive shifting problem into a straightforward exercise of filling empty spaces. Looking at the diagram, we establish 3 pointers to track our positions. We place pointer 1 at the last actual number in list 1, pointer 2 at the last number in list 2, and our master pointer, P, at the absolute end of the empty space. Because array indices start at 0, we find these exact starting coordinates mathematically by taking the total length of the elements and subtracting 1. With our markers set, we build our primary loop. We instruct the algorithm to keep running as long as both lists still have numbers remaining to be evaluated. At every step in this loop, we look at the values currently targeted by pointer 1 and pointer 2, and we determine which number is larger. Whichever list has the highest value wins the round and slides its number directly into the empty slot waiting at our master pointer. Once the number is parked, we slide our master pointer and the winning pointer one space to the left. This ensures continuous progress without data loss, setting us up perfectly for the next comparison. This diagram fast-forwards us to a common edge case. The first list is completely exhausted, but our second list still has numbers waiting. How do we handle these remaining elements now that our main comparison loop has finished? We introduce a secondary cleanup loop. Because the leftover numbers in list 2 are already sorted, we simply sweep them straight into the final empty slots at the front of list 1. But consider the alternate scenario. What if the situation is flipped, and our second list runs out first, leaving untouched numbers in list 1? If elements remain in the first list, we write 0 extra cleanup code. Because we are merging directly into list 1, those leftover numbers are already physically sitting in their perfectly sorted final positions. Watching the completed logic run uninterrupted, the efficiency of working backward is clear. Let's lock this down into a reliable mental framework for your next technical interview. Step 1. End pointers. Mathematically set your markers to start your merge from the absolute back of the arrays. Step 2. The battle. Continuously compare the values and send the absolute largest number to your master pointer. And step 3. The leftovers. Sweep up any remaining numbers exclusively from the second list. Master this sequence, and you can reconstruct the perfect in-place merge in any programming language.